So we want to start off with, what do we do in calculus? And I break it down into three things that we actually do in calculus. Number one, we describe stuff. We spend a lot of time before calculus getting ready to describe stuff in calculus. But one of the main things that we do is we describe stuff. In Calc 1, this would take the form of describing functions. There's a lot of functions that we know what they look like. We know what linear functions look like. We know what quadratic functions look like, and exponential functions and logarithmic functions and trigonometric functions and so on. So one of the ways that we describe stuff is describe of functions and their graphs. So here, if we talk about functions, we're making a big restriction on ourselves. We have two variables, x and y, and we're making sure that that relationship is a function relationship, where one variable is a function of the other. So something like y equals f of x. We also describe stuff by equations. We know some relationships between two variables cannot be expressed as a function. So for example, the equation for a circle is x squared plus y squared is equal to the radius squared. We can't write that equation where y is a function of x or x is a function of y. Because when we try to solve for x or y in that equation, we have to do a square root, and square roots lead to plus or minus, and that leads to not functions. So also equations. And I guess for this example, as an example, or for this category, we can use as an example, x squared plus y squared is equal to 25. There's a circle of radius 5 centered at the origin. Here we can't write y as a function of x or x as a function of y. We need two functions to describe this relationship. The other way that we describe stuff, although we do very little of this in Calc 1 and Calc 2, which is going to be more important now, is to describe a curve in space with parameters. So here's that same circle. Oops, I had a radius of 5. Here's that same circle with a radius of 5 centered at the origin, written in parameters, parameterized. Where the x coordinate is 5 cosine of t, the y coordinate is 5 sine of t, and that includes a circle. So once again, I'm not getting away with, even though I'm writing one expression for the circle, I am not getting away with one function. I have one function describing x and another function describing y. Note that the x squared plus y squared equals 25. We can make two functions for x and two functions for y. What we normally do is write y as a function of x. We like the horizontal to be the input and the vertical to be the output. We also like to put the x on the horizontal and the y on the vertical. There's no reason that it has to be that way, except for the fact that's the way we do it most often. So there's no reason that we have to drive on the left side of the road. But it would be a huge disaster if we just started to switch that up. So starting on February 1st, 2022, we're going to switch the side of the road we drive on. And many people would die. So just as a side note, because it becomes more relevant, it becomes relevant later on. When we write the equation x squared plus y squared equals 25, we can write this as two functions of y, where y is equal to the positive square root of 25 minus x squared, or y is the negative square root of 25 minus x squared. These two functions together will make up one circle. The plus square root of 25 minus x squared will give us the top half of the circle, and the minus square root will give us the bottom half. But because we have to get over this y is always a function of x business, we have to stop tying ourselves to this y equals f of x function business. We can also solve this equation for x. The same thing happens. We're going to end up doing a plus and minus. But I can write this equation in terms of x as x is the positive square root of 25 minus y squared. And x is the negative square root of 25 minus y squared. But in this case, we're not making a function top and bottom. We're not looking at the top and bottom halves of the circle. We're saying that x equals this function of y. So we're going to get the left and right, other way around, right and left semicircles. So the positive is where x is positive. This is going to be the right half. And the negative square root will be the left half. But if we draw a full circle, the top half and the bottom half, then we can't write y as a function of x because it fails the vertical line test. There's a vertical line that has the intercept the graph twice, and therefore y cannot be a function of x. What that means is that on the circle, each x input has two outputs, and we can't make a function out of that. Each input can only correspond to one output. That's what we need for a function. This is important because you want something like your grades to be a function of your percentage of points. It would be uncool if f of 88% was equal to A for one student and f of 88% was equal to B for some other student. You don't want the grade to be not a function of your percentage of points. You want each input to produce one output. Any questions? So that's one of the things that we do in calculus. There's a lot more to it than this, but we describe stuff. We just learn how to describe stuff in multiple different ways. With the words, like when I said a circle of radius 5, send it at the origin. When I do a picture of it, I do a picture of it in my mind. Or when I wrote this equation form, describing it in words, describing it in equations, describing it in pictures. All different ways of just describing things so that we can communicate our ideas. Number two thing that we do derivative stuff. Graphically, we think of this as the slope of the tangent line. We can also think of this as the instantaneous rate of change. It sounded like I was going to put a third one on there, but I wasn't. So I just was using the wrong inflection at the end of the previous sentence. So for derivatives, we can think of a slope of the tangent line. At a point. We can think of the instantaneous rate of change. Here are some things that we think of when we think of derivatives. And we also think about, we also do integrals. And when we think about integrals, we think of the area under the curve, or we can think of the integral of a rate of change as being the total change. I want to add this above an interval to the area under a curve. Mostly because we're going to change what our set of inputs is. Right now, when we think about integrals, when we're integrating a function of one variable, it doesn't matter that we specify an above an interval on the x-axis. Because the only way to subdivide the x-axis is into intervals. Start at A, end at B. But if we take as a set of inputs points x and y, now we're going to have to come up with a way of describing a collection of inputs that come from a two-dimensional plane. And that's not just going to be start at A, end at B. We can have a bunch of points on the plane that form a circle, or that form a square, or that form a rectangle, or that form even the space between the area between two curves in the XY plane. There are a lot more interesting ways to get a region in the XY plane than there are intervals on the x-axis. So we want to include this above an interval business when we generalize. Any questions? Comments? Deep thoughts? All right. The other thing that I want to add to this integral business, we think of integrals as area under the curve and above an interval. There's more that we want to think about when we think about integrals. We want to think about integration as multiplication, but one of the factors is variable. This is how we want to think about integration. Integration is multiplication, but one of the factors is variable. We saw a lot of applications of integration back in Calc 2 when we were studying integration. We studied lots of different examples of integration, what we could use it for. Area. Let's see. Let's just go through chapter 8. Area is length times width. We also calculated volume as cross-sectional area multiplied by height. We also calculated distance as rate times time. We also may have calculated work as force times distance. You also may have calculated force as pressure multiplied by area. You also may have calculated mass as density times volume. And what did all those examples have in common? They're all just multiplication. Any of those calculations, if I have constants for my two factors, I just multiply them to come up with what I'm looking for. If I have a constant rate and amount of time, I multiply those two to get the distance. If I have a constant force over a distance, I just multiply those two to find the work. It becomes a calculus problem if one of the factors becomes variable, in particular, continuously variable. So when we're accelerating or when we're driving along, our velocity is not going to be constant. We're going to have to speed up, we're going to have to slow down, we're going to have to come to a stop, and we're going to have to accelerate again. And when we accelerate, we don't just start going 60 miles per hour. No one goes from 0 to 60 in 0 seconds. Tesla can try it all at once, it's never going to happen. Although I gotta say, like 2.5 seconds is pretty impressive for a car that weighs like what, 15,000 pounds. They're electric cars. Really. I thought of that because there's a Tesla staring at me, and I feel intimidated by that thing. It's got very angry headlights. Like, oh, listen, don't give me that look. You have to admit that you have bad build quality. Tesla do not know how to put a car together. I know you're very popular, but that doesn't mean good. You know what I mean? Anybody been in a Tesla? The build quality is questionable. And if you think the build quality of Teslas is good, then I'm really glad that you like your car, but it's blinding you. The amount that you like your car is blinding you. Or you're looking at it too close. Like the panel gap, like you could fit your face through, so I can understand. You know what I'm talking about? On the Tesla Model X, it's the worst because they have the two doors, the front door and the back door, and they want the two little chrome plates to line up. I have never seen the front handle and the back handle line up. They're always off. That was the worst decision they could possibly make. That is going from like a guy saying, oh yeah, let's just make one thing and then they'll be like connected. And no one said, dude, those are on two different parts of the car. They're never gonna line up. And someone's like, oh, it'll be fine. And then like everybody who's ever actually built a car before said, you're never gonna get those to line up. And then Tesla Model S says, it'll be fine. It's overcomplicated anyway. There's only like what, 3 or 4 hinges between the structure and where these things are supposed to line up. It'll be fine. And it's never fine. I'm sorry if you've never seen how badly those door panels line up for the Model X, but now it'll be the only thing that you see. And I'm really sorry if you have a Tesla Model X. Yeah. Yeah. Yeah.
And you're going to and it wasn't say like that's not the bad. The one that they got never had it. And then they like have to
yeah. I can imagine that because they're a new car company. So, and they just don't know how to build cars yet. No, apparently not. Because Tesla, I think, considers itself more of a tech company than a car company. And in tech companies, so let's just build it. You know, this will cause widespread destruction. This shall. And then, anyway, what are we talking about? Oh yeah, sorry. So, at least with the Model 3, they're like, okay, let's just do a traditional door, door handle, door, door handle. They won't have to line up, which is good because they don't. It's like it was designed by someone who's never actually tried to hang a door. Has anybody here hung a door in their house? Not like gone to Home Depot and like bought a pre-hung door. The hard part is actually making the door go into the slots on the hinges and not be like at an angle so it doesn't close, or at an angle so it doesn't close, or too far over so it doesn't close. That's the trick. And we just see a door in a door frame and hinges and go, this is easy. But you should go do that sometime. It's not as fun as it sounds. What are we talking about? Oh yeah, stop distracting me. Integration is multiplication, but one of the factors is variable. And you know, how does these cancel, but there it is. Integration is multiplication put one of the factors to the variable. And more importantly, continuous. Now, these are the same things that we want to do in multivariable calculus. We just need to upgrade that first section where we are describing stuff. And the way we did that yesterday was to say these functions in their graphs, when I write y equals a function of x, we are talking about a one-dimensional curve in two-dimensional space. So in a function like this, we'll produce a one-dimensional curve in two-dimensional space. An equation in two variables will also be a one-dimensional curve in two-dimensional space. By not forcing it to be a function, we could do things like make a circle. With parameters, we are also going to be looking at a one-dimensional curve in two-dimensional space. You can see it's going to be in two dimensions, because there's an x and a y. And we're just plotting points x and y, so that's going to make a nice curve for us. So once again, we're creating a one-dimensional curve in two-dimensional space. Once we have that idea, when we talk about the slope of the tangent line, when we talk about derivative stuff, we do the slope of the tangent line. So if I've got a function, the derivative is a local thing. It's happening at a point. So there's a derivative telling us the slope of the tangent line at a point. We have this one-dimensional curve in two-dimensional space, and the derivative is telling us which way it's pointed. So the derivative is telling us the direction that the curve is headed at a given point. So here we've got a slope of 1. That means at this point x equals 2. And it looks like the graph is headed in the direction of slope 1. A little bit later, since the graph seems to be flattening out, it's still increasing, but it'll be less than 1. That'll be the direction. And because we're just stuck in these two dimensions, we can describe directions with just one number. And we use the slope, rise over run. So we say that the direction is the amount of up divided by the amount of over, the rise over run. We can do that because there's only two directions, horizontal and vertical. In the category of integrals, we have the area under a curve and above an interval. And the definite integral tells us the area under the curve and above the interval. So the top part is the curve. And the bottom part is the interval. Notice that in both the derivative and the integral, in the derivative and the integral, when you look at the graph, the symbol tells us the stuff that we need. So when we say the slope is f prime at c, it's saying take f prime, the derivative of the function, and evaluate it at the point c. Evaluate it at the point c. That's when we say in c. We need when we see f prime of c. In the same way, the integral is telling us the function to serve as the variable height and the interval from a to b, which is a set of values that we're plugging into the function. So when we look at the integral symbol, we see that we're calculating this f of x dx. That's just area is equal to length times width. Length given by the function, width given by the delta x, before we use an infinite number of rectangles, and px when we're using an infinite number of vectors. So this definite integral symbol says evaluate this expression f of x dx for all the values of x between a and b. That's what we're being asked to do. Just plug in all the values from a to b into the expression f of x dx, and that'll give us the integral. That'll tell us the area. The reason that we want to think about it in this way, we want to see that we're evaluating this expression f of x dx at all these values listed in the integral symbol, is because we need to upgrade our thinking about integration. We need to describe a region in two-dimensional space that will plug into, say, f of x, y, dx, dy. Evaluate this expression at all these values. Now you might be thinking it's not fair to stand in front of the screen and point at the projection because it's not showing up on the recording. I assure you, I did the exact same thing when I was working from home. I would make some kind of gesture that is not on camera because the camera's like way over there, and it just wouldn't get recorded. And so everybody would have to use that. Any questions? So that's the way we want to read what's going on in this integration expression. Here's the expression we're evaluating. This is the multiplication, length times width. We need to evaluate this expression at all these values from a to b. So the f of x dx is the expression that we're evaluating. The integral from a to b says do that for all the values of x between a and b. The upgrade starts by looking at functions of two variables. So we got to talk about the multivariable upgrade. We're going to start with a function of two variables. I don't know why I'm shouting everything today. I think it's because I have a second cup of coffee. I'll shout. So let's think about a function of two variables. Now for an input, we're taking a bunch of points from a plane, from the xy plane, and we're evaluating them in some function to come up with one number, because we're making a function. We're starting with functions like we usually do. Input an x and a y, output a height. And so the graph of the function of two variables is going to produce a surface in three-dimensional space, because each point on the plane corresponds to a point on some surface. So when we see z equals f of x, y, we need to think of this as a two-dimensional surface in three-dimensional space. Imagine a two-dimensional surface in three-dimensional space. We got to think about what derivatives are going to look like in this environment. Now, instead of just having a one-dimensional curve in two-dimensional space, I've got a two-dimensional surface in three-dimensional space. What does it mean when we talk about the direction? What is the scope of the tangent line going to be now? So in the case of derivatives, instead of a line tangent to the curve at a point, we're going to produce a plane tangent to the surface at a point. So instead of a line tangent to a curve, we'll have a plane tangent to a surface. In terms of integrals, we're going to imagine this surface sitting above the xy plane. And so instead of area under a curve, where we had a function of one variable, now that we have a function of two variables describing some surface, we're going to pretty much just upgrade everything by one dimension. We're going to be calculating the volume under the surface and above a region in the xy plane. So for integrals, instead of an area under a curve and above an interval on the x-axis, we'll calculate the volume under a surface and above a region in the xy plane. We're going to structure our symbol the same way. We'll have some f of xy instead of dx will be dA, and dA will be a small piece of the region. And then over here on the integral side of things, we'll have to come up with a way to describe the region that describe all the values of xy that we plug in to the expression. So our volume f of xy dA, f of xy this is just a calculation based on multiplication again. Volume is equal to cross-sectional area multiplied by height. So I take dA, this little piece of area from this region R, and I multiply it by the height, which is given by the function of xy. So this represents volume multiplication of area times height. The integral over the region R, those are all the values of x and y that I plug into this expression so that I get the volume that I want. Just like these are all the values of x that we plug into this expression, just the area that we want. If we can properly think about integrals and where integrals come from and what we can do with integrals, rather than looking at what we can do with integrals as a bunch of little things, we can see the overall picture of what integration is about. And integration is just multiplication, but one of the factors is variable. Any questions? Comments? And you may be thinking, didn't you say most of this stuff yesterday? I'm like, oh, actually, I think I said all of this stuff yesterday. And I'll probably say a good portion of it again tomorrow. Because we don't hear things once and remember them. We hear them thousands of times and then remember them. That's how songs get stuck in your head. You don't just hear the song one time and then it's stuck in your head. You hear the song billions of times and then they get stuck in your head. At least that's what somebody says. Or say, somebody once told me, now that song's in your head, you're welcome. If you're worried, Leach, that's just going to make us hate you. I'm the math teacher. I already know how this goes. I already know that I'm the villain. I just haven't released my minions out onto the world yet. I mean, I'm the math teacher. Clearly, I'm the villain. Question? Yes. Class started yesterday, but I wasn't set up to record, and that's why I didn't get it recorded. And that's the other reason that a lot of this sounded familiar. Yeah. You should imagine that the homework is all there for the whole semester. All your homework is ready to go. So if at the end of the day, you're about to go to bed and you realize you haven't done any math that day, your day isn't over. You need to go do some math. Now, you might be all caught up on your homework as far as the due dates go. You might even be a chapter or two ahead. That doesn't mean that you're done with the homework. So the homework doesn't stop until you're standing up here and explaining it. I'm just kidding. The homework will stop on May 20th. Of course, if you're not done with the homework on May 20th, it still just stops. And needs to be done. Any other questions, comments, thoughts? Is this display going to work? But this is the way I'm going to do notes. This way I have a written record of all the notes. All right, well, that's going to do it for today. I will see you all on tomorrow. Everybody have a good day. Get started on some homework. Thanks for playing.